Okay. Hi, everyone. Thanks for coming to today's Q-Farm seminar. So I'm very happy to present today's speaker, Mohammad Hafezi. Mohammad is a professor at University of Maryland in physics and in electrical engineering, electrical and computer engineering departments. And he's also a fellow at the Joint Quantum Institute there. He did his undergraduate work at École Polytechnique in France, and his PhD was at Harvard with Michel Luque. And he's made numerous contributions to quantum optics and topological physics and quantum information science. So today he's going to tell us about many body invariants from statistical correlations of randomized measurements. And well, before he starts, I just want to remind you, please put your questions into the chat box, and during the talk, I'll try to interrupt Mohammad and unmute you so you can ask your questions or ask your questions for you if they're not so complicated. Okay, so thank you, Mohammad.
Okay, thanks, Amir, for the invitation. It's always nice to be at Stanford and seeing you guys, not seeing you guys. I am going to give this talk. This is actually the first time I'm giving this talk, and also giving a talk and not seeing the audience is already weird. So please ask questions whenever you have them, and then we will figure out how to answer them. The more questions I get, the better feeling of how I'm doing. So I would like to talk about this measurement of many-body invariance. And the story basically is that we have quantum simulators. We have access to these quantum simulators. They're growing in size. And the question that we're asking is that we have these many-body states, how we would like to characterize them, and what are the efficient ways to measure these many-body features. So some of them, some of these questions are new. We did not think about them because we were thinking about electronic systems and many-body physics in terms of real material. But now with these quantum simulators, actually there are interesting questions, not only from a practical point of view, but also from a fundamental point of view. So the first part of the talk would be actually that fundamental point of view, that specifically, if you're interested in the many-body Chern number that I define and describe, how we can measure it. If I give you just a single wave function, if I don't allow you to do linear response theory, if I don't allow you to change the parameters of the system. So this was the question that we worked out with my student Zipe and my postdoc Hossein in collaboration with my colleague Maysam Barkeshli, and most likely some of you know him since his time at Stanford. And then the second part of the talk would be on, once we do this fundamental understanding, how can we go and measure it in a real quantum simulator, in particular using statistical correlations of randomized measurement. And that was a collaboration with Innsbruck group, in particular Andreas Elben, a student of Peter Zoller, and Benoit, and also my former postdoc, Guanyu Zhu, who's now at IBM. Okay. So as I said, the question is that giving a quantum simulator, what are possible and efficient ways to characterize and measure quantum many-body states. So usually we have the picture of linear response paradigm. So either I shine some light at different frequencies and then look at the reflection transmission, and then I learn about what's going on in the system, measure optical conductance or dynamical structure factor, static structure factor, etc. Or we measure transverse conductance in the context of quantum Hall effect. When you have a two-dimensional electron gas, you have a perpendicular magnetic field, and then you look at the transverse conductance. And then we see sometimes interesting features like fractionalization or quantization of the transverse conductance. Now that's kind of the state of the art since 1980s. Now we have access to quantum simulators. So these are a bunch of figures from places that I have either collaborated or affiliated with, so they're very biased. There are many other quantum simulators around the world in different platforms, ion trap, superconducting qubits, and also Rydberg atoms. So now with these things, I have two, I want to make two remarks: that linear response might not be applicable in some of these implementations. And some of them has to do with, the fact that sometimes we are dealing with bosons and we are dealing with neutral systems sometimes. So the conductance, measurement of conductance is not applicable. Second is sometimes we don't have the required disorder. Some of these, for example, the emergence of plateau in fractional quantum Hall is due to the presence of finite disorder. We don't have that. These systems are finite in size. So that actually has not prevented people to think about these questions. As of a few weeks ago, there was a paper how to measure quantum Hall drift in small systems. But as I said, it's a kind of sometimes a technical and fundamental issue. But more importantly, in these quantum simulators, we have access to the wave function. We have access to the full wave function. So we can, in principle, measure and apply full quantum state tomography. Of course, we would like to avoid it. If we are interested in just the scalar, I don't want to do an exponential number of measurement in terms of number of qubits, but we have that full access, and that kind of inspires us. Maybe there are other ways to measure many-body parameters. So I divide these kind of schemes to measure many-body features into two categories: ancilla-based and ancilla-free. Ancilla-based is basically a simple idea that I have a two-dimensional, three-dimensional quantum simulator, and I couple an ancilla either to a part of the system or to the entire system. And then depending on the state of this ancilla, I apply some operator. And then by measuring that ancilla, I can measure some many-body features. So basically, this is a generalized version of old Ramsey spectroscopy. We have the ancilla, we have the wave function, we apply Hadamard gate. We have two branches. In one branch, we don't apply any operator. On the other branch, we apply some operator. Let's say that, for example, just the evolution with some Hamiltonian. And then we apply another Hadamard gate, and then we get this quantity. So this can be a many-body wave function. The psi doesn't have to be a single state. It can be a many-body state. So that would be a many-body overlap. It allows us to measure some many-body operators if this H is a many-body operator. And I can just list some of the examples. So a while ago, again, this is biased, very much related to the works that I've been involved with. One of them was, for example, anionic interferometry. If I have an ancilla that, depending on which, if the ancilla is, for example, in 0 state, I do nothing to my system. If it's 1, I apply a string operator. One can actually do this anionic interferometry. Another example is that if I want to measure the entanglement spectrum. So if you don't know, the entanglement spectrum is something simple. If I have a state, I partially trace over part of the system. The rest of the system can be described by a partially traced density matrix. And this density matrix, the same as a Hamiltonian, can be diagonalized. It has eigenstates and it has a spectrum. And the spectrum of that density matrix carries interesting information. For example, some topological character of the system. And then what we realize is that after a paper by Sitloyd and company, that if you have access to the swap gate, exponential swap, you can evolve a density matrix with e to the I rho t, similar to when you can evolve a system with e to the I ht, you can access the spectrum of H. Here, if you have access to the e to the I minus I rho t, you can measure the spectrum of rho. Another example is a quantum clock and measurement of OTOX, out of time order correlator. You should be familiar with these folks. at Stanford. We were again inspired by that work. And then we looked at the question again, if I want to measure such an operator, in which not only I have e to the minus ht, but also e to the plus iht, how should I do that? And again, I couple an ancilla to my system. Depending on the state of the ancilla, the system can go forward in time or backward in time, and then perform a many-body Ramsey spectroscopy. So basically, that are a bunch of examples that if we have an access to an ancilla that is coupled to the entire system, it's very rich and we can measure many of these many-body features. Unfortunately, this is very hard to do in an experiment. I hope some of the experimental colleagues are actually working on this, but push more forcefully in that direction. But apart from these ancilla-based, it would be nice to have also some ancilla-free schemes. And that is actually the topic of this talk. So specifically, we would like to measure this many-body topological invariant, this fractional many-body Chern number in a quantum simulator. The first part of the talk would be how to extract this many-body Chern number from a single copy on a disk. So usually in topological system, you theoretically assume it's on a torus, it's on a cylinder. Now we want to be more concrete. If I just give you a single wave function for a single parameter on a disk, can I measure many-body Chern number? And by single copy, I would like to emphasize that I don't mean just a single wave function, because we believe in quantum mechanics, I have to have access to many copies of the same wave function, of course. By single copy, I mean a single wave function for a single parameter, but many copies of that, if you like one version of your wave function. And then in the second part, can we actually realize it in an experiment using randomized measurement in an ancilla-free setup? So what is the many-body Chern number? Before going forward, if there is a question, please let me know. Just look at whether there's a pop-up in the channel. There is a chat. Okay, well.
There's no questions yet.
Yeah, there is no question. Okay, there was Nancy's actually comment. Okay, so many-body Chern number. What is a many-body Chern number? I usually put my system on a torus. Most of my particles are on a torus. It's either a many-body system or a single particle system. It doesn't matter. It's a periodic boundary condition. So it's defined by two twist angles, theta x and theta y. And depending on this theta x and theta y, I have to diagonalize my Hamiltonian and I get a wave function. So this wave function, again, can be a many-body wave function, and it can be degenerate or non-degenerate. But it's always a function of theta x and theta y. Once we have that dependence, we can define a Berry connection like this. So we take the derivative of this wave function with respect to one of these parameters. From that, we can define a Berry curvature. And then if I sum over this Berry curvature over the entire possible values of theta x and theta y, which is basically 0 to 2 pi for theta x and 0 to 2 pi for theta y, and then that by itself also makes a torus, then we get the Chern number. And if it's a many-body state, then that would be a many-body Chern number. So now what's the physical significance of this many-body Chern number? The Hall conductance is related to that, and it's given by E squared over H bar times the Chern number. If the system has degeneracy, S, then we have to divide this C by the S, and that's where, for example, you get 1/3 conductance when you have a fermionic system for n equals 1/3 filling factor. So this filling factor is the number of electrons divided by number of total magnetic flux in the system. Your Chern number will be 1. By definition, this is always an integer number. But since your degeneracy is 3, you get the 1/3 Hall conductance. If it's bosonic, 1/2 hardcore bosons, then again you get Chern number 1, and then your degeneracy is 2, so you get 1/2. This statement is almost always true, but not always. So this S sometimes is not exactly the total degeneracy of the ground state. If you're interested, we can talk about that, but that's kind of like a detail. A more important point is that recently, people realized that actually you don't really need to, it was a common knowledge, but now it became more understood that you don't really need to sum over the entire possible values of theta x and theta y. And in fact, Hall conductance is local. So if you have access to just this curvature, basically for a vicinity of some theta x and theta y, then the corrections to the C is exponentially small in the system size. So basically, if I have access to, if I can vary this twist angle a little bit around some value of theta x and theta y, that's enough. But still, you need to vary them to get that. So basically, you still need to use this linear response. But now we would want to reduce that. We would like to have no dependence. I just want to give you a wave function for a single theta x and theta y. How can I do that? In order to do that, we have to go back and revisit Restes formula. It's a way to measure the Chern number, and for that,
sorry, Mohammad, I have a question. What do you mean? What do you mean you still need to vary the twist angle? What do you mean by that?
So this was a curvature. So if I give you theta x and theta y, so if I just have a psi for one value of theta x and theta y, I cannot measure, I cannot create f, because f is a derivative with respect to some theta. Does that make sense?
Yeah.
Yeah. So I just have access to one psi for one value of theta x and theta y. Is that possible? So Laughlin argument, he related the Hall conductance to the insertion of flux in an element. So this is my two-dimensional electron gas magnetic field is perpendicular. I'm interested in transverse conductance, basically the current in the radial direction, electric field in the angular direction. And what we do is that we generate this electric field by varying this magnetic flux from, let's say, 0 to 2 pi. That would generate an electric field in the angular direction, and that would lead to a current in the radial direction. So that's how we can see the Hall quantization of Hall conductance. But later on, we realized that for neutral systems, since we know that current is related to the polarization of the system, then one can think of that current as actually change of the polarization. Now, another point is that if I'm in a periodic boundary condition, if my radial direction is periodic, this polarization is not well defined. After the famous work of these folks, that P usually is just the polarization, it's related to the charge times the displacement. But this displacement Y is well defined if I don't have periodic boundary condition. If I have periodic boundary condition, then that displacement is defined mod L, L being the length of the system. That's why these folks came up with this polarization. It's a modern way of defining polarization. So now I would like to relate J to this and then to that. And what Rest realized is that instead of measuring the Chern number the way that I defined in the previous slide, you can just vary phi and then look at the polarization, how the polarization changes, basically to get the Hall current. And then what we see here is that we don't now require two variables to be changed. We just need one variable to change, this phi. And now I have reduced the problem of changing two variables into changing one. So that's what Rest did. So now the claim, our claim in this paper is that we would like to actually reduce even 1 to 0. We would like to just have a one wave function that is given, let's say, for theta x and theta y equal to 0. And by applying some operator, these W's here, I simulate the effective non-zero twist angle. And then I again plug this polarization operator over here, and then have the swap operator. And then this gives me again the same polarization that we have in the rest of the formula. And if I take the derivative of that polarization with respect to theta, I get the same Chern number as the previous slide. Okay, so the goal is basically to justify that this expression is valid and makes sense. In particular, I would like to show that how Swap operator gives non-trivial manifold. I told you that I want to start with the state that is sitting on a disk, not on a torus. And I'm saying that applying the swap operator, which I will describe in detail, would create an effective torus for me. And then applying this V and W operator gives me the right operator to create a non-zero theta, non-zero phi, and then simulate the effect of this polarization operator, such that when I put them together, I get this expression. And if I take a derivative with respect to phi, I get my Chern number. Is that okay? I think I have another question. Yes, here these are two. The question is that are theta x and y strictly scalar parameters? They are scalars. Okay, so that was the question. So that's the claim. I want to justify that claim. In order to justify that claim, we have to use the language of topological quantum field theory. Okay, so I'll try to do that in one slide. So what is a TQFT? Is a theory that it's independent of on small deformation of a space-time metric. Basically, I would like my observable to be insensitive to the details of my manifold. So if I deform my manifold, my physical observable, I want them to be intact. So given a closed space-time manifold, the TQFT defines the topologically invariant path integral. Okay, on a manifold with boundary, and let's say if I had this manifold and now it is this boundary, the boundary defines the state that is living at this boundary, and it can be thought again as the value of the path integral on M. So what's an example? An example is that let's assume that I have the TQFT on a sphere S2, so the path integral is on S2. The state would be on the surface of this manifold. So it would be at the rim of this spherical cap, S1, which basically is a circle. Okay, and now you can think of this inner product in this situation will be just, I have my bra, so psi bra would be this cap, and then psi prime will be, the ket will be this cap. So if I combine them together, that would again give me this Z. So Z will be the union of these two manifolds. So now, usually in quantum Hall effect, as I said, we start with the state on a surface of the torus. So my wave function, instead of now being defined on a circle, I would like it to be defined on a torus. So the wave function, the bra and the ket, should be defined on the surface of a torus. So in order to create those, similar that here I created this circle by starting from a point and then growing into a surface, and then from that surface circle going back again to the point. Here you create it by starting from a minus t, and then from a solid surface, and then blowing it basically out. This dimension is t inside the torus, so you go from minus t to 0. So on the surface, I have created the wave function on a torus. This t squared is torus, and then for the bra is the same thing. Now, if I want to look at this path integral, which will be the inner product of this with this, we get S2 cross S1. The way to see it is the following. If I have a circular, I have this X, so if I can cut the system at any point in X, I will end up with a disk, and the disk can be deformed in the disk that we had in the past. So basically, the T direction and the Y direction will be the similar thing that I had over here. So I will create a S2, and then the X that I have cut at each point will just come along. So basically that would be just a circle. So it would be S2 cross S1. So now our goal in the end would be to have the wave function on a disk, not on a torus, but then for the moment to just understand the those expression. Let's just focus on the case that we have the wave function on a torus, and then reinterpret this rest the polarization that I had in the past. So now I would like to understand how this phi comes about and whether I can write this in terms of an operator. So we have to go back to the Chern-Simons theory. The Chern-Simons theory, response theory, allows us to basically explain the Hall conductance in a very simple way. If I assume that my electrons are not coupled to electromagnetic fields, like Maxwell's them, but just to a term that is described by this action, then if I vary this action to get my current, then we see the Hall conductance immediately. So that's the beauty of Chern-Simon response theory, that I don't need to think about anything. If I just believe in this low energy response of the system, then it basically describes this. Now, I would like to figure out how I can interpret this phi, this psi at phi non-zero, and this operator. This is a little bit technical. I think this is the most technical slide that I have. So I hope that's okay. So first of all, let's understand how this phi emerges in this system. So this phi will be the, again, if at the top corner, I showed the system on the previous slide. So I have my state on the surface of a torus. And now I want the psi to be defined for a non-zero phi. That non-zero phi can be described by a symmetry defect of this form, by a vector potential that is zero in the t direction and also in the y direction, but in the x direction in non-zero, and it has this singularity. And then, so basically that would be the that would be my partition function or path integral. So basically, this guy defines when my phi is non-zero. Now, I would like to interpret also this operator. If you look at this operator, is nothing but just a bunch of scalars and the density. Okay, so the density, we know that we can just write it as the t component of the current. So then basically jt, and then in order to get the right form, then the rest. And J is coupled to A, the A should take a form such that I recover this operator. So by choosing A, now in this case A1, to have this form, then I can exactly have this expectation value. And since we have done this identification, then this expression will be exactly the expression that I have over here. So now overall, if I divide this expression by this expression, and then calculate it through Chern-Simons theory, then I exactly get this e to the I p over q s phi. And then if I take the derivative of this polarization with respect to phi, you see that we end up with the right Chern number that we have. So what we did was that we just took the rest of the formula, we kind of reinterpret that rest of the formula in terms of this TQFT. And that is important for later on. So that was part one. How these operators, how can I define such an operator, this operator and this operator, that can give rise to this expression for a torus. But then I have not told you yet how one can make a torus out of a simple system. So that's where the swap story comes about. Now I would rather relax the fact that I start with the state on the surface of a torus. So how can we make a torus out of a simple system? Using swap. So this is the discussion of space-time surgery. So again, let's assume that I have my wave function on a circle. So this is the circle over here. And then I would like to, instead of identifying each of these points, by each of these points, I would like to come up with a different way of identifying them. It's like, for example, in the MPS formalism that you contract indices of matrices in position, instead of contracting each position in the bra with the same position in the ket, I would like to now identify some of these positions in the opposite direction, let's say from the left side to the right side. So I would like to identify the states from the ket over here to the bra over here, and the bra over here to the ket over here. So this is another way to see it. So we open an eye over here, an eye over here. This arrow should be identified with this arrow, and then these two double arrows with these two double arrows. In order to see it more easily, let's rotate this by pi. So now I have just rotated this by pi. Now the double arrows are pointing this way, and then the one arrow pointing that way. And now I identify them. I identify this guy with this guy, and the bottom with this bottom. And what you see is that it will create a handle, because this now should go over here. So this is exactly just like that. And then if you look at this a little bit more and then deform it, you see that it's a torus. So we started with something that was S2, was a surface of a sphere. Now we end up with something that is a torus. So we didn't have any handle, and now we have a handle. Now we can do this with two copies, like that was one wave function, one wave function ket and one wave function bra. I can do this for two. And now instead of identifying this with this, I identify one part over here to another part over here. So again, this is another exercise. So we again open these eyes, and then I identify them. I have to rotate this by pi, I have to rotate this by pi, and then connect them. And then if I do that, then you see, again, this, if I deform it, it's again the torus. So we can start even with two copies and make a torus, and that is actually what is more relevant for us. Now, okay, I just showed that if we start with swap and do this partial swap, you can create a torus, but that was not the whole point. We wanted to start with something that is not compactified, that's not periodic in one direction, and not yet make a torus. It turns out that you don't really need the periodic boundary condition in the x direction over here, in this x direction over here. Even if it's a sheet like this, and I follow the same kind of rules that I had over here, and I identify this by that, etc. Then again, I can create these handles or wormholes, if you like, and then create an effective torus locally. So if I don't care about the boundary of the system, I have locally created a torus in the middle of the system. And that's what basically allows us to have a non-trivial topology now. So I have now two ingredients. The first ingredient was the symmetry defect that I had in the previous slide. And now this partial swap that allows me to create a non-trivial topology. Now I put them together. So I have this system from previous slide. And now I decorate it with my operators that I had in the TQFT slide. This is the same polarization operator. And now this is the one that gave rise to non-zero phi. So I can start with the 0 phi, and then this creates a non-zero phi. So one important observation is that these two operators are local in time. You see that there is no time dependence. They just depend on the density. So I can just apply them. They're just, they don't have any dependence on time. It's just flat in time. You see, it's at time 0 and then time 0. Another way to see this is to connect them like the previous slide. And then I have region 1, region 2, region 3. And then now I have these twist defects that, symmetry defects that this is the W that I had over here. Now it forms a circle, and then the V over here. So this is a pictorial way of looking at this. A mathematical way of looking at this is the following. I have two copies of the wave function. I apply these operators. I apply the swap operators. And then that should give me the polarization that I want. Now, if you want to change it as a function of phi, you don't need to change your wave function. You just apply another operator on it. Some technical reason, there is also this thing should be also normalized. So there is a normalization at the bottom. But since it's real and we're just interested in the phase of this guy, you can just think of the numerator. Then the numerator is just there to make it correct mathematically. A bunch of remarks. Two copy requirement is optional. It's only important for later schemes that I'm gonna present. The W defect plays the role of the twist angle. That's what I mentioned. The partial swap makes handle so that defects cross each other. So if I did not make this swap operator, I could not cross these defects. So this defect should cross this one, and that's actually gives rise to the non-zero to measure this chain number. The second swap operator that we have over here is optional. Why? Because if I said that the crossing is important, these guys have crossed each other over here. You just don't need to have this over here. This line can go to infinity over here and go to infinity over here. So I can just forget about this expression, the second swap. So even a one swap can do that. And then, as I said, V and W should cross each other. So if there is no question to this point, I will move on to the numerical part and then numerically show some numerical evidence that this expression is actually correct.
There doesn't seem to be any questions. I had a question a few slides back, on where you were, maybe if we can go a few slides back. Yeah, like P and Q. I was just wondering what P and Q were.
I can just say that. So yeah. So this is basically the Hall conductance. So you have two integers. You have one integer in numerator, one integer in denominator. Okay. Let's say it's a 1/3, and then P will be 1, Q will be 3. Okay. So my Hall conductance is C over S, which is equal to P over Q. I brushed over some subtleties of the S, and what is S, and in what situations it's equal to the degeneracy of the system, etc. But for simplicity, P over Q in equals 1/3 will be just 1/3. Or for hardcore bosons, for n equals 1/2 will be just 1/2. Should I go ahead?
Yeah.
Was that
okay? Good, thanks.
So now the numerical results. So as I said, this 2-copy formula was just the way that we needed for later on in the implementation, but 1 copy would be enough. So basically you give me the wave function, I apply these operators, this V that was generalization of the polarization, and then this twist angle generator, and then the partial swap. And then once you apply it numerically, you see that it works. So this is the argument of that polarization. And then if I look at its slope as a function of phi, then it has the right form for different models. So for n equals 1/2, for n equals 1, 2/3, for bosons, fermions, etc. And this is all a cylinder. So single copy, a single formula on a cylinder. If I have 2 copies in a bilayer cylinder, it's the same expression that I showed in the previous slide, and again, it works fine. Okay, so far we know it analytically that it should work, and numerically it should work. And now we also numerically checked if we just don't we don't compactify the one direction. We only compactified one direction and didn't compactify the other direction. Now let's not compactify both of the direction. Analytically, we could not do this. We don't understand this. This is still an open question. But if we assume that we just now not compactify both of the directions, so it's basically on a rectangle or a disk, and then numerically investigate what happens to the polarization, we see that again it's fine. So if I look at the slope, it gives me the right direction. But then for some situation, it has a bump. So I cannot just use the slope. I have to basically integrate it from 0 to 2 pi, and I get the right answer. So it's a little bit more susceptible to finite size, etc. So I cannot just take the derivative, but I have to take the integral, and the integral gives me the right answer. For bilayer, if I have 2 copies, again, it is correct. And then we checked for a bunch of cases for n equals 1/2 hardcore bosons, for 2/3 bosons. And the reason we did this was that, again, the subtleties when S is not equal to the ground state degeneracy, and when it's different from that. And we see in all cases it produces the right answer. Now, okay, that was basically the first paper that I mentioned. How, if I give you a wave function, is it in principle possible to extract the many-body Chern number? Now I would like to show that this is actually experimentally relevant, and one could do it in an experimental setup. So if you look at this, if you look at stare at this expression, is not that scary. There are a bunch of operators over here, but it's not that bad. It's a bunch of local density operators. People know how to apply them. And then this swap operator. And we know that the swap operator has been implemented, at least in correlatum systems. In particular, if I have access to two identical copies of the system, and then I allow some tunneling. So this was one copy, this is another copy. If I allow some tunneling for some time, and then I do the parity measurement, then I can, in principle, measure the expectation value of the swap operator. So that was done in the group of microstrainer using correlatum systems. And in principle, one could think of it in a circuit QED. For example, at Yale, people have done control swap. So in principle, it's possible, but it's really hard to have two identical copies. So here, it was only just one mode. Here, it was a few modes. So it's really hard to make sure that you have two identical copies. So in order to avoid this problem, if we don't have access to two copies, what can we do? Fortunately, we know that we can actually measure the swap operator by randomized measurement. And that was first done for René entanglement entropy measurement. René is basically the purity of the partially traced density matrix. You can write it as trace of rho squared, or you can write it as trace of a swap operator between two copies, two identical copies like that. And we used kind of this trick to measure the SPT in variance. That was, I initially wanted to talk about that, but I realized the talk is already too long, so I did not talk about this. I apologize. So why this is the case, I can give you some mathematical reasoning, but a very simple reasoning why on Earth, if I apply some random unitaries and then do some measurement, I get a swap operator, can be understood in the following way. So imagine that I have a density matrix rho. I apply some unitary operator U and U dagger, because I have two indices, and then I project it into some state S, okay? Now, it's a random unitary, it's hard random, so you apply any U that you like, and then you repeat this experiment and then average over. So I put this bar over here, means that I do this experiment and I project it over S many times, okay? So what do you get? You should get identity, because you basically randomize, regardless of what state you started with. You have applied a random unitary, so you start in a random place. So if you do this many times, you just have to get identity, or something that is proportional to identity. So basically, you start with the system, but since you are averaging over U, you are pulling out this U from a random ensemble. Then I get this. Basically, I get the contraction of rho, and then this is state. So this is 1 and this is 1. So it's proportional to 1. Now, what if I do it for 2? Basically, I start with 2 state. I apply random unitaries on them, and then I look at the statistical correlations. So this I described it over here. I have rho and rho. I apply the same random unitaries, so this should be S or S and S prime. And then I do the same thing. I repeat it for many U's, and then average over them. Once I average over them, there should be no dependence on U on the right-hand side. The only thing that I'm left with is a bunch of contractions with some permutations. So the identity permutation would just be trace of rho times trace of PS. But then I have also this permutation that can give me, that takes this index and then contract it with this one. That gives me trace of rho squared. And this gives me trace of rho squared. And that's how these folks came up with the way of applying the random unitary and then doing statistical measurement to measure rho squared. So we use the same machinery to apply the swap operator. So if you bought this, then I convinced you that one can measure this swap operator. The only thing that now we have to do is to to apply this V and W. If V in our situation does not commute with these unitaries, so first I have to apply that to the wave function and then apply the unitaries. But then since W commutes with the region that I'm applying these unitaries, then it can be done after post-processing. So to summarize, I can tell you that what the protocol would be. I start with these two wave functions. I don't need to have them at the same time. They can be two separate experiments, but it's just easier to illustrate it. So this is one experiment. This is a separate experiment. Oops. So we said that we apply this operator in some local density operator. Then we apply our random unitaries on one of these regions. As I said, we only need to apply it on one region. We don't need to apply it on both regions to create a crossing. Then we just do a projective measurement on state B and B prime. And then we repeat it many, many times for different U's such that they constitute random unitaries. And then we send them to the computer and then we post-process them. So that's the result. So we post-process them. So now this T tilde, the claim is that this T tilde is equal to T that we defined in the previous slides. We have applied V by applying that local operator, and then we add this post-processing. So basically I have these data, this data that comes from my measurement, and this O that is given by this expression. And this expression, I make sure that depending on the number of particles in each region, let's say region 2, I multiply them by 5 such that now I have applied my W in the post-processing, and I sum over all possible outcomes for wave function on one of the experiments and the wave function on the other experiments. And once I sum over them, then the claim is that these two expressions are equal to each other. So let's look at it numerically. These are the numerical results for nu equals 1/2. Bosonic fractional Chern insulator. These are hardcore bosons. So we expect that the Chern number would be 1 for S equals 2. So we apply the random unitaries. This can be done with some quench dynamics, some tunneling and on-site potential. So this is a 6x8 system. So this is a lattice of 6x8 system. And I have these two regions. And I apply these random unitaries. And then we see that the probability of getting Chern number 1 converges to 1, the expected value, when we increase the number of random unitaries. So in this plot, I assume no measurement error. So we have actually access to the full statistics. But in practice, this is a quantum system. So every time you make a measurement, you have to repeat it many times to develop all the statistics. So if we add that, the number of times that I have to repeat my measurement, then again, we see the same thing. So now this is with measurement error. And of course, it scales exponentially in the number of sites and particles that I have. And we see after a while, and since then a logarithmic scale, it converges to 1, the number that we are interested in. And if you put some numbers, then it's not that bad. Of course, it's exponential, but in a course of few minutes, let's say, I don't know, if the speed is like 10 kilohertz, if you just do it for a few minutes or an hour, the data is possible. So you don't have to wait for the age of the universe. So these are actually, this scheme is relevant for disk devices. It cannot work for a thermodynamic large system. And this is just the small part, how to prepare it that I skip. I just want to summarize and give an outlook. So I showed in the first part how we can extract many-body Chern number from a single copy on a disk. So I could simulate the effect of twist angle by applying some operator and then making these non-trivial geometry, non-trivial topologies using partial swap. In the second part, We talked how we can apply random unitaries and correlated measurement, statistical correlations to distill that Chern number. So what I did not talk about and outlooks, and would like to know what happens, is that whether these kind of techniques could be applied to other invariants, other many-body invariants. I cheated a little bit in the beginning. I mentioned that we don't need to really need any information about the Hamiltonian. But then when I making a connection between TQFT and these twist defects, I said that these should be density operators. So can we actually even forego that? Can we do it more directly? I provided numerical evidence that our scheme works for rectangular system or a disk. I did not provide analytical argument through TQFT that it works for rectangular systems. So that's still an open question. Another interesting question is that other type of space-time surgeries might be possible with this randomized measurement. So in this randomized measurement, I did the simplest one, which basically identified this with this part of the wave function, that with this part of the wave function. But you can do it in a more creative way. So you have X, Y direction. You can connect any of these X to any of those Ys and create even a non-orientable manifolds. Are they interesting? Are they useful? And the last and very more important point is that the scheme that we presented here was exponentially hard in the number of qubits. Is it possible to find more efficient ways that does not exponentially scale with the number of qubits? And that would be a question to ponder. Okay, thank you very much for your virtual attention.
Thank you, Mohammad. Thank you for a very nice talk. So I'd like to open up for questions. If you have any questions, you can raise your hand or put it in the chat room. Maybe I'll start out with a question. So this swap operation, it seems like it's like a fairly non-local operation that you need to do on. So is that, have you thought about like how that can be done in experiments, or how much, what the errors are or things like that?
So this part, so if I want to do it, if I have access to 2 copies, maybe I went a little bit fast over here. So if I have access to 2 copies, then one can apply this non-local operation. So that was done in Marcus Greiner's experiment. So if I have 2 identical copies, the evaluation of swap operator is nothing but doing tunneling and parity measurement. So I can just put the systems next to each other, let them tunnel for half a period, and then do parity measurement. That needs 2 copies. But what I was trying to motivate here is that this partial swap can be done if you allow me to use these random unitaries. It's very expensive. So in Greiner's experiment, they just did this and then measured it, and then that's good. But now here I have to repeat this experiment so many times for different use to simulate the effect of swap. And your question about the error would be over here, that you see I have to do an exponentially large number of measurements such that it converges to the number that I'm interested in. So that's the. So it's a so I'm simulating, it's kind of funny because if I want to do a partial swap, can you see me?
Yeah.
No, okay. So if I want to do swap, it's a non-local operation. So what I'm saying is that I'm doing actually this non-local operation by not doing it, applying some random unitaries on those regions, and then doing projective measurements, and then doing correlations many times.
I guess my question, those unitaries can be local, those random unitaries?
So those unitaries can be local. For swap is actually for having these 2 design that I did not get into it. One can actually simulate it and see that even a local operation would be okay? Sorry, I misunderstood your question. So you're asking about these U's, whether the U's can be local.
Yeah. So any two design on those two parts would work. So it can be.
Yes, but the problem is that even within that region, I have to have a global U. So it's not global over the system, but still, if I'm claiming that it's a global U in that sub-region, then I have to do that. So in this situation with tunneling and random on-site, one can do it. But if you don't allow me to do tunneling and random potential, and you just allow me to do local, it is possible, but then the price is that you have to wait longer. So the scaling is not that good.
I see.
I don't have the number off the top of my head, but Zippe actually did that simulation. And maybe I should cite it next time I give this talk. But it is possible. Yeah.
Okay. I'm gonna, so there's some question. I'm gonna unmute some, Xiaoyu, I'm unmuting you so you can answer your question.
Oh, hey, thanks for the talk. I was just wondering what's the, I wonder if the chain number is well defined, let's say for a small number of qubits. And if so, like what would be the meaning of it, like physically? Somehow I feel to see where this topological concept like emerges in maybe like, let's say 3 or 4 qubits. It seems like a miracle.
That's a very good question. It's actually related to the first part of the talk that kind of made us think how small is the small, okay? So the second part was just about the measurement. Just think about the first part. How small a system can be that I can claim that it still has a Chern number and it has some meaning, okay? So naively you would say, okay, these are well-defined in thermodynamic limit. But then we know that actually thermodynamic limit is not required. So for example, Hall conductance is something local. So as long as I can do properly my local measurement, then the corrections to these local measurements are exponentially small. Okay, so can I come up with some way to characterize the system and then see that the Chern number could be defined for a small system? And that's indeed one of the motivations of the first part of the talk, that let's forget about the disk, etc. If I have a cylinder and you do this the way that I define the Chern number, you define the Chern number not through Resta formula, but through our formula, you see that you get an invariant. So even for a small system, you can still define it. But of course, at some point, these things don't work out. And we have a long discussion in our paper how small you can get and how these things, because I talked about the overlap of this symmetry defects, etc. They should be large enough. And the typical wavelength, the typical length scale that you need to know is the correlation length. So for example, for fractional quantum Hall would be magnetic length. So as long as the system is a little bit larger than the magnetic field, it seems that you can actually define it and it works fine. That's indeed one of the motivations of the work, how small it's okay.
Thanks. So more questions. Okay. Seems like people are a bit shy today.
I hope it was not too abstract, the first part.
Yeah, I think it's good. I found this idea of the, you know, like I wonder if you thought about these randomized measurements, how to extend them to, you know, other physically interesting quantities. What you think about that? Like.
So one of them was that we are thinking right now is this the first example that I gave for this ancilla-based measurement. So that this doing anionic interferometry, that you need an ancilla to do these string operators. So you have this ancilla, and then you apply this string operator, and then you can do and check that you have a Tori code, etc. Now we just showed that this is some of these non-local operations is possible by doing swap and random unitary. So we are thinking whether that might be actually possible to do that as a test, that you have the right code.
Okay.
Yeah,
that sounds pretty cool, especially for these NISC systems. Okay, so if there's no more questions, I think I'm gonna stop the recording now, and then